Hey, welcome back. This is the review video for Test 2 and Calc 3 on Chapter 12. So I'll give you sort of the question pool here. 12.1, web assigned problems 1 to 4, 8, 9, 12 to 14, and then 17 to 22. 12.2, looking at 1 to 8, and then 12 to 18. 12.3, looking at 1 to 8, 12.4, 1 to 3, and then 6 to 12, and then 12.5, 5 to 17. There is a formula sheet this time, so formula sheet provided. Basically, it's provided on Blackboard, so you go to Blackboard. Go to course content, and then there's your formula sheet. It's in two formats. It's the same thing in both. It's like the PDF version. So you can either copy this out with a printer or copy it down by hand. On the day of the test, I'll want to see your formula sheet along with all your other papers, though. So, anyways, you can have this out while you're going through while you're doing your review, and so it would be a good way to rehearse for the test. Right, so you'll have that. Let's dive in here and start looking at some problems. So 12.1 is when we introduced vector valued functions. So you're dealing with forming vector value functions. I probably won't have you plot anything drastic. In the plane, maybe, yeah, I'd have to think about that. No space curves. I'm not going to have you plot something in space. That'd be ridiculous. But definitely representing plane curves with vector value functions is a possibility. And then we also have limits, limits and continuity. Okay, so domain, limit, continuity, a little bit of graphing, and representing functions with vector value functions, plane curves with vector value functions. Okay, so let's look at 12.1. And probably the most fundamental thing you could do is create the equation of a line given two points. So like number 4, a point -8, -3. And all I'm going to do is like pick out 1 or 2 problems from each section like I did last time. But any of the problems in the question pool are fair game. Just want to warn you. You know, a big shout out to my neighbor who is chopping down the tree that is on partially on my land and on his land. The tree is about 200 years old. It actually has a tree house up in it from probably about 70 years ago. My mom loves that tree, but it's putting a lot of leaves on his land, so you could see why he would be so upset about it with all the leaves and everything. And so he's cutting it down. So you hear a chainsaw in the background. You send a big thank you in his direction. Okay, so without further ado, let's go ahead and take a look. We want to find a vector value function that represents this line segment, and we want to also then give the parametric equations. So the vector value function R of t, basically you need kind of a slopiness thing. And you get the slope by just taking the difference of these components. So -1 minus 8, -1 minus -8 is 7. -9 minus -3 is -6. -5 minus -2 is negative. I'm looking at my work here, and it looks like I made a mistake in my work, but this is correct. So, you know, -5 minus -2 is -3. And then you go plus, and then put the starting point, a vector pointing at the starting position, which is -8, -3, -2. So that is the vector value function. If you rather, you can write it as one vector, you know, go 7t, -8, comma, -6t, -3, and then -3t, -2. Okay. All right, so there's your vector valued equation for the line segment. Now I got to get the parametric equations, and that's simple. You just take the components and set them equal to x, y, and z. So x is 7t minus 8, y is negative 6t minus 3, and of course then z would be negative 3t minus 2. So fundamental thing that everybody should be able to do. Okay. Anyways, let's look at maybe a limit problem. So find the limit, it's number 18. Limit as t goes to 0. This is, I mean, essentially it's more of a review problem more than anything else. Do you know how to take a limit? Let's just take the limit of the components. And it's pretty simple, so long as you learned your lessons in Calc 1 and Calc 2. Anyways, plus e to the negative 2t. Okay, and for most functions, if they're continuous at the point, all you have to do is substitute in the thing the t is going to. So in this case, you can plug 0 in. E to the 0 is just 1. So you get 1i plus, then the limit of this critter may be a little bit more complicated, right? So let's take that to the side and take a look. Limit of sine of 5t all over 5t as t goes to 0. So in this case, that form is 0 over 0. That's called indeterminate. So if you plug in 0, you get 0 over 0. It's not working like it should, right? So what you can do is, we had an identity in Calc 1, but you could always just do L'Hopital's, which we learned in Calc 2. So cosine, take the derivative of cosine of sine of 5t. You get 5 cosine 5t all over 5. Then you could simplify limit as t goes to 0 of cosine of 5t, and then substitute because cosine is continuous at 0. So cosine of 0 is just 1. Okay, so you get plus 1j. And then the last guy, if you plug in 0, e to the 0 is 1, so that would just be plus 1k. Right? So you should be able to do limits. You should be able to identify intervals of continuity, that sort of thing. Okay, let's go on to 12.2, and that's where we introduced derivatives and integrals of vector valued functions. And it's pretty simple. If you remember, all you have to do is basically take the derivatives of the components or integrate the components. With integrals, you know, you have that constant of integration is now a vector, basically. So you have to be a little bit careful of that issue. Let's look at number 5 in the homework. So just very simply, can you find a derivative given a vector valued equation? So we have 6 square root t, t squared square root t, and then ln of t squared. Okay. I'm going to rewrite this stuff so it's a little easier for me to take the derivatives. T squared square root of t, that's the same thing as t squared times t to the 1/2. We have like bases there, so you can just add the exponents. You get t to the 4/2 plus 1/2 is t to the 5/2. So we have t to the 5/2, and then ln of t squared. The derivative then, 6 times 1/2, so I'm just doing a power rule, t to the negative 1/2, 1/2 minus 1. 5/2, t to the 5/2 minus 2/2 is 3/2. And then finally, the derivative of the natural log is 1 all over the guts times the derivative of the guts. So you get 2t there. And then we could clean it up a little bit, multiply the fractions. You could leave negative exponents, that doesn't bother me too much. So 5/2 t to the 3/2. But you should be simplifying, you know. So 2 all over t. Go to the end answer on that last guy. Okay, let's look at an integral. Let's try number 16. I won't be asking for smoothness. It doesn't, I mean, it comes up, but not as much as we would think. It's usually just an assumption. We assume we have smoothness. 16, we have an integral, a definite integral. Okay, so the integral from 0 to pi over 3 of secant t tan t comma tan t comma 2 sine t cosine t. So I expect you to have all the basic integral rules memorized. That first guy, secant t tan t, that's secant. The second guy is the ln of the absolute value of secant. And the third guy, I have to think about that one a little bit. I'll probably have to do a u sub, bring out the 2 sine t cosine t. So do a little u sub work here. I'm going to let u equal the sine, and then du is cosine t dt. So cosine t dt. So I can replace the cosine t dt with du, and I can replace the sine with u. I get that. And then integrating u, I get 2u squared over 2, in other words, u squared. And then back sub, so I get sine squared t for that part. And I have to remind myself to evaluate all these. So I get sine squared t, and then I'm going to start evaluating. So secant is really 1 over cosine. Cosine of pi over 3 is 1/2, so 1 over 1/2 is 2. So you get 2 minus secant of 0, cosine of 0 is 1, so secant of 0 is just going to be 1 as well. Then ln of the same sort of business, so ln of 2 minus ln of 1. And then sine squared of pi over 3. Sine of pi over 3 is root 3 over 2, so sine squared will be 3 over 4. And then sine of 0 is just 0, so you get that. 2 minus 1 is 1. ln 2, I don't know, I'll just leave it like that. ln of 1 is 0, and then 3/4. Okay. And I'd prefer if you just left it as ln 2. Don't get an approximation. Just leave it that way. That's fine. Okay, so from there, 12.3, we get into the issues of the physics sort of end side of the coin. You had velocity, acceleration, and the projectile motion function. If I do give you a question with projectile motion, I will supply the formula for projectile motion. In particular, let's look at one of those. So let's sit down here to one of those. I think I'm going to do number 6. Yeah. Okay, so I'll give you this formula if I give you one of these questions. So that's still, an if. But it's the magnitude of the initial velocity times cosine of the initial angle t, comma, and then the magnitude of the initial velocity times sine of the initial angle t plus h minus 1/2 gt squared. Make sure all your units are good. And I'm not going to have you convert like miles or feet to miles or anything, or miles to feet or anything like that without giving you the conversion formula. Just okay. So let's look at number 6 here. And use a model for projectile motion. G in this case is 32 feet per second. Per second. So determine the maximum height and range of the projectile fired at a height of 8 feet above the ground. So h is 8. Initial velocity of 800 feet per second. So v sub 0 is 800. And then the angle is 45 degrees above horizontal, so theta is 45. And then once you go around the 3 decimals. This probably might be a little longer than what I'll put on the test, but still you should be able to do it. Let's take a look at our official kind of position function in this case then. So it's going to be 800 cosine of 45 degrees. That's just root 2 over 2. So let's cut to the chase. That would be 400 root 2t, and then sine of 45 degrees is root 2 over 2 as well, so 400 root 2t plus 8 minus 16t squared. We're trying to determine the maximum height and then the maximum range. So the maximum height, I want to work with the y component here and maximize that. In other words, I got to take its derivative, find the critical point, and then plug that back into the y formula. So anyways, y prime would be 400 root 2 minus 32t. So setting it equal to 0, I would get 32t equals 400 root 2, and then t would equal 400 root 2 over 32. If I simplified, that's 25 root 2 over 2. Okay, then I'm going to plop that back into the y function, this thing again, and you end up going y of 25 root 2 over 2 equals whatever that is. And I already figured it out earlier. It's 5,008 for the max height. Okay, and it's in feet. Then the max range, a little bit more work, because you're going to have to use a quadratic. So first you have to find the max range, because this is a projectile. If you think about it, it's going up and then it's coming back down. So the max range is going to be when it hits the ground. In other words, when the height is equal to 0, or the y value rather. So not the initial height, but when the y component is equal to 0. Okay, so again, I have to work with this guy, and I have to set it equal to 0. So I have 0 equals negative 16t squared plus 400 root 2t plus 8. I'm going to simplify that a little bit, divide by 8, move everything to the other side. I get 2t squared minus 50 root 2t minus 1 is 0. I'm going to use the quadratic formula on it, believe it or not. T is negative 50 root 2, so that would be 50 root 2, plus or minus the square root of. It's going to give me 2 answers, but I want the bigger one, right? So probably the positive one is the only one you need. So negative 50 root 2 squared minus 4 times a times c all over 2 times a, which is 4. Computing that turns out to be 35.369 for the time. And then for the range, you just plug that into the x component. So x of 35.369 is going to be 400 root 2 times that. Let's just, I got that figured out already. It's 20,000, 7.997. Okay. Right. So yeah, be able to compute accelerations, velocities, and if I call upon you to do so, you should be able to draw the vectors for velocity and acceleration. The next part then, 12.4, was about the unit tangent and unit normal vectors, and then the acceleration components. So 12.4, you should be able to find all of that stuff. I'm not going to put any of the hard ones on there, like number, what was the hard one? Number 4, I did that one in the video. I won't put something like that on there, but something like number 3 is definitely fair game. So I give you r of t equals t comma 6 over t. And we want to evaluate the principal unit normal vector at 2. So I first need the derivative and then the magnitude of the derivative. Okay, so that'd be 1, and then 6t is the same as 6t to the negative 1, so that'd be negative 6t to the negative 2. Then the magnitude of the derivative is going to be the square root of 1 plus 36t to the negative 4. Let's rewrite that as 1 plus 36 over t to the positive 4. Get a common denominator. And then the square root of a quotient is a quotient of the square root, so I'll have t to the 4th plus 36 all over the square root of t to the 4th, which will be t squared. Then I multiply r prime by the reciprocal of the magnitude of r prime, and that will give me the unit tangent vector. So that will be t squared all over the square root of t to the fourth plus 36, comma, negative 6. In that case, the t squares will cancel out, all over the square root of t to the fourth plus 36. I'm gonna go ahead and kind of cheat a little bit to find my principal unit normal vector. Right. So first off, I'm going to get t of 2. That will be 4 all over 2 times 2 is 4 times 6. 16 plus 36, 36 plus 16, 2, 1, 3, 4, 52. So it seems like 4 goes in the 52. 1, 4, 1, 2, 3, 13 times. So it's going to be 2 root 13, comma, negative 6 all over 2 root 13. And then we could rewrite that as 2 over root 13, comma, negative 3 all over root 13. Okay, so to get the principal unit normal vector, I have to basically look at the graph of r of t. So looking at the components, x is t, y is 6 over t, so y must be 6 over x. And I could do a little graph. So it's one of these rational functions. At 1, it's at 1, 2, 3, 4, 5, 6. At t equals 2 or x equals 2, it's at 3, 1, 2, 3, right here. And so the orientation is going downwards like this. This is the point we care about. The tangent vector, the unit tangent vector given there, has positive and then negative. So it should look like this. That would be t. So the principal unit normal vector that we want is the one that points inwards into the inside of the curve where the direction of travel is headed. And if you think about its components, it has to be positive, positive. Okay. So our unit normal vector, then, you just swap the components and make one of them negative of what it was, and we'll end up then with 3 root 13. So you just make a negative negative 3 over root 13, which is 3 over root 13, comma, 2 over root 13. And that will be your answer then for n of 2. Okay, so you could do it the long way where you just take the derivative of the unit tangent vector and then find the magnitude of the unit tangent vector. But that turns out to be kind of computationally exhausting. So this may be a better route to go if you can handle graphing the thing. Okay, let's also look at number 7 where we're dealing with some components, the acceleration components. So this just comes down to guessing the appropriate component formulas. Avoid having to find that principal unit normal vector at all costs. So anyways, number 7, find basically a sub t, a sub n at t equals 1. And our function r of t is t squared, comma, 2t. So this is the kind of thing you would need that formula sheet for. And looking over there, I'll probably use for a sub t the v dot a thing. That tends to be the one you go to, v dot a or the magnitude of v. Okay, so I need the velocity and the acceleration. So the velocity is just the derivative, of course, 2t, comma, 2. The acceleration then is going to be 2, comma, 0. And then I can compute a of t. I also need the magnitude of the velocity, the speed. So that will be square root of 4t squared plus 4. And okay, so a sub t is going to be v dot a. So v dot a is 4t plus 0 all over the magnitude of the velocity, which is the square root of 4t squared plus 4. a sub t of 1 then is 4 all over square root of 8, which is 2 root 2. So we're ending up with 2 over root 2 for that component. And then get the other component. So I'll use the square root formula for that guy. Because acceleration, the magnitude is going to be real easy to find. So I have a square root of 4 plus 0, so it's square root of 4, which is 2. So the normal component is just going to be the square root of that magnitude of a squared, so that's 4, minus the a sub t squared. So that would be 2, and this is then evaluating at 1. Right, so 2 all over root 2 squared. I get the square root of 4 minus 4 over 2, which is 2, so I get square root of 2. And both those answers are the same. They don't look the same, but if you rationalize, you'll just get square root 2 for both of them. Okay. Okay. So make sure you can handle those kind of problems. Let's move ahead to 12.5. And 12.5, we have the arc length formula, and then we have the curvature. So I'm not providing the arc length guy, but I do provide one of the millions of curvature formulas that they threw in your lab. So anyways, let's take a look. So I think I want to do number 14. So you should be able to find arc length. You should have that formula memorized. But the curvature formula is not necessarily. Let's look at one like number 14. I don't think I did. Did I do one like that in my notes? Yeah, maybe. Seems like I did number 15 in my lecture. So let's try number 13 as opposed to that one, and see what happens. So number 13. Actually, let's try number 12. That one looks annoying as heck. So r of t equals e to the t cosine t, comma e to the t sine t, comma e to the t. We want to evaluate the curvature at 1, 0, 1. You should note that the t value that corresponds to that point, it must be 0. Because if you put it like 0 in that first component, you'll get 1. If you put in 0 on the second component, you get 0. Put 0 on the third component, you get 1 again. So let's look at the curvature formulas and see what they give us. I don't think we have too much of a choice here. I think I'm going to use the cross product one. I'm not going to put things in terms of S. That's usually a little bit more complicated than I want to go at. There's no way I'm going to use that third formula because I'd have to find the principal unit normal vector, and I hate that thing. So I don't know. But let's try the cross product one and see how obnoxious that is. So I need r prime of t. Or probably in the process of trying to get it, it'll snowball, and I'll say let's try something else. But let's take a look. So r prime of t, I got to do a product rule. Derivative e to the t is e to the t times cosine t, and then plus leave e to the t alone. The derivative cosine is negative sine, so I get negative e to the t sine t, comma. Then the next guy, derivative e to the t is e to the t sine t, and then plus e to the t cosine t. And this is just going to start in the snowball already, right? And then we have e to the t. It may be better just to deal with the unit tangent vector, the derivative of the unit tangent vector, but I don't know. Yeah, this is gonna, so let's get the magnitude of r prime of t. This is going to be the square root of this thing, this first component squared. So I'll have to FOIL that thing. It'll give me e to the 2t cosine squared t. And I wouldn't put something that's this intense on the test. That would be evil, unless I do it accidentally. I wouldn't mean to. e to the 2t cosine squared t plus, or rather minus 2e to the 2t cosine t sine t plus e to the 2t sine squared t. I'm having to use the whole page here. Then foiling the second part, I get e to the 2t sine squared t plus 2e to the 2t sine t cosine t plus e to the 2t cosine squared t plus e to the 2t, just squaring the z component there, and then that would be, well, I guess it's, that's it, right? Because we don't have nothing in the denominator. So what is this thing? These guys cancel. I'll have 2e to the 2t cosine squares plus 2e to the 2t sine squares. You can factor out the 2e to the 2t, and then you have cosine squared plus sine squared in there. So you'll just end up with 2e to the 2t, and then plus e to the 2t, and then that will just be the square root of 3e to the 2t, and that's just square root 3e to the t. So let me make sure that's right. Okay, so there's 1, 2 of those. So you'd have 2e to the 2t cosine squared t. There's 1, 2 of those plus 2e to the 2t sine squared t. And then, yeah, so then there's just a plus e to the 2t. And so I factored these out, and the rest, the sine squared plus cosine squared is 1. And then plus e to the 2t, so 3, yeah, okay, that seems right. Then you could form the unit tangent vector, t, which would be then doing a little bit of canceling, cosine t minus sine of t all over root 3, comma, sine of t plus cosine of t all over root 3, comma, 1 all over root 3. And then you could take we need the derivative of that thing. So that would be negative sine t minus cosine t all over root 3, and then cosine t minus sine t all over root 3, and then 0. And then I think we have everything we need to get the curvature for the one particular curvature formula. K equals magnitude of t prime of t all over magnitude of r prime of t. So I need the magnitude of t prime of t, basically. So the magnitude of that thing then is going to be square root of foiling that guy. You're going to get sine squared t plus 2 sine t cosine t plus cosine squared t plus foiling the second guy gives us cosine squared t minus 2 cosine t sine t plus sine squared t, and then all over 3. Okay, so this would end up being the square root of, these guys cancel, then we have 1, 2 sine squares plus 1, 2 cosine squares, factor out the 2, Pythagorean identity, and we get root 2 over 3. So the magnitude of r prime of t was root 3 e to the 2t, I think. Root 3 e to the, no, just root 3 e to the t. So the curvature is root 2 over 3 divided by root 3 e to the t, which would be root 2 over 3 times 1 all over root 3 times e to the negative t, which would be root 2 all over 3 e to the negative t, apparently. And then we're evaluating at 0, so k at 0, I hope, would be root 2 over 3. We'll see. Drum roll. Root 2 over 3. Yeah, so, okay. I'm not going to put something crazy like that on the test. You'd spend the whole time doing one problem. So, but you should be able to figure out curvature, using whatever formula that's required of you. And so that will do me for the review. As usual, thank you for watching, and we'll see you next time.